Hi, my name is Felix Egner, and I'm a PhD researcher at KU Leuven in the field of noise and vibration engineering. Greetings from Belgium. No, not these kind of simulations. Acoustic simulations. A simulation is an approximate imitation of the operation of a system. Now, let's take an example to illustrate this. We engineers or physicists use simulation whenever real-world measurements are not feasible. So let us design the acoustics of a new concert hall. The concert hall itself is our model, and some key characteristics are the geometry of the space, acoustic properties of the materials involved, and environmental influences like noise from airplanes. As the concert hall doesn't exist in reality yet, we can't just go there and take measurements. We must rely on an approximation, in our case a computer model. After specifying geometry, material properties and sound sources, we simulate the model. We compute its evolution in time. This way we obtain features of the room like its reverberation time, damping against environmental noise, and transfer functions between the stage, where the orchestra is playing, and the audience. Based on the results of our simulation, we can adopt the concert hall design and iterate the process until the results are satisfying. With auralization methods, even the sound you would hear when listening to a concert in our new concert hall can be emulated. Without simulation methods, it wouldn't be possible to test such a huge amount of designs. But bear in mind, the quality of a simulation relies on the assumptions being made. It remains an approximation, and making a simulation requires profound knowledge about the considered system. An interesting aspect about acoustic simulations are the methods being used to describe the physics of sound propagation. Generally, there are three different types of approaches: geometrical acoustics, element-based methods, and statistical methods. All rely on a mathematical description of sound propagation, but each method is suitable for different types of applications. The previous example with the concert hall will usually be simulated using methods of geometrical acoustics. These methods treat acoustic waves similar to a ray of light. The wave propagates in a straight line and gets reflected from surfaces. Geometrical acoustics allow computations in large geometrical spaces and a good accuracy at higher frequencies. Because of the ray assumption, these methods cannot account for diffraction effects at lower frequencies. In contrast, most engineering applications are simulated with element-based methods. Thereby we divide the model into a huge number of small elements. Some applications are sound absorber designs and radiation of machinery. Here we have complex geometries and a relatively small problem size. And coupling to other physics fields like structural mechanics is important. Unfortunately, the simulation of high-frequency content requires small, so a lot of elements, and therefore a large computational effort. Statistical methods find their use mostly for quick assessments of sound transmission through structures. And yes, we find acoustic simulations also in simulation games. Especially for virtual reality, a realistic impression of sound is important. To make you hear a virtual room realistically, the before-mentioned auralization techniques are used. To conclude, simulations are model-based approximations of reality. Various acoustic simulation techniques allow to mimic the physical phenomenon of sound. They are of great help whenever sound needs to be predicted. For example, where the acoustic properties of rooms or machinery shall be designed. Acoustic simulations save us a lot of time and enable whole new worlds of design possibilities. Now stay tuned and have a look at the other episodes of our Acoutect Web-Series.
Hi Felix, good morning. What are you going to talk to us about us today?
I will talk about acoustic simulations.
Okay, why acoustic simulations are important?
They are important because you can't just measure everything. And if you can't measure something, you want to simulate it.
Okay, great. So, and also, like, who was your childhood artist, like the childhood star that you wanted to become?
The Red Hot Chili Peppers,
Okay.
full group.
Okay.